Okay. Can you see my screen?
Yes, sir.
Okay,
Yes, sir.
cool. So the agenda for today is there was a discussion around time complexity in Thursday's lecture. So we will actually look at it in a little more detail, like how to measure the time of a command, right? And then we'll do some experiments after doing that measurement, and then we'll look at some nested loops example on like how to break a problem statement into a nested loop solution. And then if time permits, we'll also look at some gotchas, like some errors you can make when writing loops. So let's start with the the time thing. So there's a command in Linux called time. So if you, let's say I'm running ls, so I want to see like how long this command takes, right, to run. So I can do time ls. So what this shows is it shows the time it took in total. So don't worry about user and sys, like user and system. This becomes more clear when you study OS, for example. But for our purpose, you can put time in front of any command to see how long a command takes. So we can use this to like figure out how slowly or quickly our programs are running. So let's look at this example, right? So what this is doing is this is taking an input of into a unsigned long integer, and then this is looping from 2 to the input, and it is trying to see if any number divides this input. If yes, then it returns that it is not a prime number. It prints that it is not a prime number. Otherwise, it prints that it is a prime number. So what we can do is we can try to, I have this prime number here, which is a pretty big prime number. So this is million, it's like 1 billion. So हिंदी में कहें तो this is like 100 crore का number, right? So pretty big number, and we are going to see how long it takes to see if the number is prime. So what I can do, Acha, so actually if I run this like this, so giving the input will also take some time, right? So it's better if I don't give the input, and instead I can directly so let's compile this again, and then let's run this. So as we can see, since the number is pretty big, it is taking some time, but it should end soon. Okay, so it's printed that this number is prime, which is the right answer. And it says that it took 10 seconds. So which is cool. So now we can look at another instantiation of checking prime numbers. So we can use this fast.c program. So the only difference is that instead of looping over to, okay, let me open slow side by side. So the only difference is here it was looping to the number, but here it is looping to square root of the number. So for 1 billion, it will only loop like 10,000 times or even lesser. So let's see how how quickly this program runs. Right, so this program ran much faster, right? So it gave the right answer, but instead of taking 10 seconds, it took only 0.5 seconds. So you can use this, basically this time command, to figure out how fast your programs are running. So far, is this clear what I did? Any questions? and I can also look at the chat.
So we have to take care of the time while writing the program.
Uh, so since this is an introductory code, like I don't think we are writing very large programs. But over time, as you grow as a programmer and as a like in more real world problems, you would worry about this. So currently this is in seconds, right? 10 seconds maybe is not much. But as you can imagine, like slow computers. So if you are writing something, then you want to be careful around how much time something is taking. But for the purpose of this course, I don't think it's a first order concern. Like the first order concern is to learn programming, but this is something to know. Like the decisions you are making in the program can affect how long a program takes. So both these programs are
Sir,
checking. Yeah.
sir, even if we realize that the program is taking long, what is the method we can reduce the time it's taking, like when it's not square root a?
Uh-huh.
Is
Yeah. So you are saying like, so for example, I wrote this program and I saw that it is taking 10 seconds. Now I want to reduce the time. So how do I go ahead and reduce it? So that is actually a very interesting question, and it's not a easy answer because for every program you cannot just put square root, right? Like otherwise the meaning would change. So there's a whole course which just deals with this, which is called Data Structures and Algorithms. Very, very, very interesting course. You will fall in love with computers when you do that course. So yeah, it's very interesting how you can take a slow thing and make it faster, making sure that both of these things are achieving the same thing. So yeah, it's not an easy answer.
Get the final answer faster with help from the mathematics. Make
Uh,
our
can you type your questions? I can't hear you well.
Sir, I have a doubt.
Yeah.
Sir, while using the time command, if we also have like a scanf command, so will it also include the time for that, like typing the input?
Yep. So yeah, that is why I had removed it. So let's try it. So here I'm now also taking the input, right? And let's say we'll give it this input. So let's compile this. Let's run this. And I'm waiting for a couple of seconds to give it the input. And now let's say I give it the input. So previously this program, like time showed 10 seconds, right? So now let's see how long it shows. So basically now it shows 16 seconds, right? So yeah, so the answer to your question is yes, it includes, so it's from when you start to when the program ended, everything is included.
Sir, does it include time of comments? Like if you type in so many commands, so does it include time of?
No, so yeah, so that is the compilation process. So when you compile this, actually, so notice here that we are running slow.o and not slow.c.
वही रास्ते में कटवा लेंगे भैया मार्केट जा रहे हैं बस मार्केट में कटवा लेंगे
Okay. So yeah, like as we can see, we are running slow.o instead of slow.c. So basically, long story short, compiler removes all your comments from slow.o. So you can write an entire story, whole script of a movie inside comments, and it doesn't matter because compiler will remove it. Okay, I hope this is clear. So basically, the takeaway is using the time command, we can measure the time of a program. So,
Sir, What is real, user and sys? I mean, real is the time taken. That is fine. What is user and sys then? The time shown after that.
This will become, but this is time taken in the system, which is basically the kernel, and this is the user. So as we can see, yeah, like as we can see, when I paused to give it input, the time in user increased, but time in kernel stayed roughly the same. So they don't even add up to real, right? So yeah, like let's not worry about it right now. For now, let's only look at this real. So I think, yeah, I was hoping someone would mention it. So no one mentioned it. So let me mention this. So basically, if I actually, yeah, we have done this already. So when I ran fast dot, where is it? Yeah, so when I ran slow.o, it took 10 seconds, right? But when I ran fast.o, it took 0.5 seconds. So but the loop was running for this many iterations in slow.o, and it was running for, does it do square root? Okay, square root. So 32,000 times in slow.o, in fast.o. So, but the running time is not a square root. So it's not square root of 10 is something like 3 point something, but running time is only 0.5. So yeah, like no one mentioned it, so it's kind of.
Yes, sir, because that is 32,000 times greater amount, so I think that's the reason.
Yeah. Okay, great. Oh, wait. 32,000 times. Is it 32,000 times?
Sir, I think uh, in the second case, the loop will no longer be the
So it is 20 times.
Yeah. So 32,000 times of this is actually 18,000 seconds, which is 5 hours, more than 5 hours.
Sir, I think the later loops are taking more time, the later iterations.
And why is that?
Sir, because the number is getting bigger.
Maybe it is calculating square root again and again, like we have written in the loop square root, so it will have to calculate that thing every time that it runs.
No. So actually, okay. So that is a proposition. So
It is calling another directory, I mean mat.h in this program, but in that there were not such thing. So maybe to fetch that thing, it took time.
okay, so we have some theories, so that's nice. So let's try all the theories. So slow.c does not have math.h. So actually it does have math.h. But someone can argue that it is not using math.h since we're not doing square root. So let's also use math.h. Then the other comment was it is repeatedly taking square root in every loop. So what I did was to pull this thing up out of the loop. And now we can try this. Okay, any other theories we should try?
Sir, tell that that the time depends on the number of calculations, not on the calculation which you are doing. Like we do plus or minus, it doesn't matter. It just count as one.
Yeah.
Like I have take the square root and I have to the plus addition, and in the MATLAB it's count both as one.
Okay, so what is your final, like, why did fast.c not take a square root amount of time? That is the thing we are discussing. So fast.c took 0.5 second and this took 10 seconds.
Sir, as the number gets big, the module takes more time.
So like when we say how much time it takes, it will be time into number of operations, right? So when we take the root of that, it will be time into root of number of operations, not root of time into number of operations. So the time remains outside and then it gets multiplied. So we directly can't take root of the time taken.
So your time is a constant, right? So what you just said is fast.o is t, which is some constant, into square root of our input, something like this. And you said slow.o is this, right?
Yes, sir. I meant that slow is not like fast is not exactly the square root of slow because
Right.
t is not getting.
Right. Yeah. So I guess, yeah. So it's kind of, yeah. So again, this is like a very hard question to predict how long a program would run, because inside the computer, there are a lot of things going on. So someone mentioned later loops are taking more time. And the reason for that is since this is a 64-bit computer. So when the calculation is up to 32 bits, it is taking a particular amount of time because it can likely use 32-bit registers. But when it goes to 64, when the number gets bigger, then it will use 64-bit registers, and it might take more time. So there's a lot of complexity that goes inside. So it is, and moreover, like compiler may be doing some interesting things and so on. So it's, yeah. So that's why, and there are constants. So in general, like we say, addition is just one, modulo is just one, but there are a lot of constants which we don't see here, but they can impact the real runtime. So to understand, but the way we generally do analysis of programs is to run the same program on larger and larger inputs. So this, I have written this measure.o. So what this is doing is it is doing a primality test on this number. And this is using the fast program, and this is using the slow program. Right? So as we can see, the number keeps growing higher and higher, and this is still pretty fast, but this number is getting higher and higher. So roughly this is growing linearly, right? So as we can see, this goes from 400 million to 1 billion. So it goes from 4 seconds to 10 seconds. So roughly we can run the same program on larger and larger numbers. And I actually have this results. So this is a previous run of the same measure.c. So we ran this program on higher and higher numbers. And this is the time the slow program takes. This is the time the fast program takes. Now, since this number is much bigger than this number, what I did here is I basically took logarithms. So this is the log of this one, and this is the log of that one, and so on. And similarly, this is the log of this. G is the log of B, and H is the log of C. And what I did was I plotted the two. So I plot H versus F, which is the orange line, and I plot G versus F, which is the blue line. So basically, so when your y is equal to x, right? So this is roughly x, right? Because there are a lot of constants. So roughly you will see log y is roughly log x. And in the other case, your y is square root of x. So roughly you will see that log y is equal to 0.5 times log of x, right? So again, this is very rough because there are a lot of constants involved, but in a rough sense, you should see that the if I plot log y versus log x, I should see the slope of this line should be around half of the slope of the other line. Right. So as we can see, the blue line is less in slope, and the orange line is higher slope. So this is basically how we study algorithms later on. So we just care about this slope. So basically, when the numbers start getting large and large, the effect of constants diminish, and the trend, we only care about the trend. So this is just a example of a simple program which we can analyze using the time command and draw very interesting conclusions. Cool. Any questions, comments? And I can also, let me see the chat. Why does 3 times are shown when you write time command? Yeah, let's not worry about this. Let's only look at real for now. Do we have to take help from mathematics to give the computer less for loop iterations? Yes. So the algorithms course, if you choose to do that, is actually, yeah, pretty mathematical. And some people joke that you do more math in CS than you do in math. I don't know how true that is, but yeah, there's a lot of math involved, as you can imagine, in speeding up programs.
So in the question where we have to find the first n square prime number, my program is taking almost 2 seconds. Is it a good program or not?
Okay. What is your question? It's taking 2 seconds and then?
Is it a good program? Because I have written it, but it is taking 2 seconds. Earlier it was taking, I think, 8 seconds. But I have introduced the variable and now it is taking 2 seconds. Can I make it much faster?
Okay, yeah, 2 thumbs up. So you are able to speed up programs. That's pretty interesting. Like, we don't expect that right now, since the goal is to learn programming. But if you are able to do that, that's pretty nice.
Can the time be reduced for this program?
Yeah, like, again, that is a very involved question, right? So it's not very easy to answer. So, like, for example, people study just one problem for decades. So for example, there was a question of multiplying 2 matrices. So the best known algorithm is still reducing. So people have been working on one problem for like 30-40 years and making progress in speeding up programs. So I can't say if what is the optimal algorithm for your problem. Maybe I can for your yeah. So there is another question, sir. Is there a fundamental limit beyond which we can't reduce time for a certain result? Yeah. So when you study program algorithms, like, sometimes you also study lower bound of time taken. So which is basically you have to spend this amount of time, otherwise your program cannot be correct. So again, that is very mathematical and analytical to figure out the lower bounds. But in general, you may not be able to find out lower bound for every problem.
So can we say that for the prime number question, square root of n was the lower bound, like those number of iterations?
No. So yeah, it's actually from IIT Kanpur itself, the person who taught me algorithms. That person gave the fastest algorithm to check prime numbers. And he was awarded, I think, Abel Prize, which is like the highest prize in computer science for algorithms. So you can check. I don't claim to understand the algorithm. It's very yeah, like this AKS primality test. It won the Gödel Prize in 2006. So this is a much faster way of checking primality, and you can attempt to read it, but I won't be able to help in the help session because I don't claim to understand this. It's very involved. So yeah, this algorithm looks like spend something like log n power 7.5, which is much lesser than square root of n. But again, like this is again not the lower bound. So someone, maybe some of you might come up with a new algorithm, which is even faster. So this is a constantly developing field, and it's a interesting yet very hard field.
And so one way to approach for prime numbers can be that from the given factors of a number we can I mean from different number we calculate remainder and quotient, and from that we can generate better next checks that can improve time.
Yeah, so now you have the tools to check it out. So you can keep, so this is a list of like, take some list of big numbers and you can play with this if you want. So write your faster version of programs and see like how long they are taking, draw the trend lines. So this is a way of drawing the trend lines and see if you are solving it faster. And if you can, that will be like a very big result. if this is faster than the best known algorithm, then yeah, you might win something very, very huge. So I think we can move on. Hopefully you can understand. Yeah.
So I am getting two different running time for a same program. I run them in a consecutive manner, and I'm getting two different times.
Yeah, so this is again, time command is specific to your machine, specific to your compiler. So you will not get the same results that is expected, but you get the same trend lines. So if you draw them.
So also there is an interesting thing, sir. When I increase the value of n, the running time decreases in one of my commands.
Oh, it might be a prime number then. And not.
No, sir. I am not running this program. I am talking about another program where we have to print the pattern like hatch, one hatch and then gap and then another hatch in a single line, like in the assignment question.
Yeah, that is counterintuitive, so that shouldn't happen. So that can happen for like small inputs. So for example, let's say in my measure.c, let's say if I give it small inputs, right? So instead of large prime numbers, I give it very small prime numbers, 2, 3, 5, 7, 11, 13. How many? 7, 1, 2, 3, 4, 5, 6, 7. Right. So now if I run this, so sometimes you might see some counterintuitive results. So like this is 3 is faster than 5. 13 is slower than 13 is fastest among all of these.
Yes, sir. Why this is happening?
Yeah, so basically in small inputs, those constants take over the size. So the constants, yeah, like again you have to study OS, so how a program actually runs. But the constants and the other decisions that your computer is making simultaneously can affect this. So the proper way to do the analysis is to run with large inputs, so that those constants don't meddle around too much. So that is number one. The second thing you should do is run it at least 5 times. So whenever you do any experiment, run it 5 times and then take the average. So for example, if I run it again, then you will start seeing, you will not see the same results, right? Okay, so let's move on, since we only have till 11:45 today. So we are done with this. Yeah, let's move to nested loops. So I want to take this a bit slow than the previous help session. I think some of you are familiar with nested loops, but many of you are doing programming for the first time. So we will take it a bit slow. So I think so far we have been looking at in the lecture as well, we have been looking at thinking about what a given program does, right? So for example, this program is a nested loop. So it is printing 4 rows. It will loop 4 times, then inside it will loop 4 times, and then it will print a new line. So basically this is print, and in the inner loop we will print star. So basically we are printing 4 stars, and then we are doing a new line, and then we are printing 4 stars, then we'll again do a new line, then we'll print 4 stars, and so on. So I want to look at it in a different manner, which is how do I write a program given a pattern, right? So let's look at it in a different manner. So let's say I'm asked to write star, and then star star, and then star star star. So basically, how should one even go about and try to do this, right? So the way to do this is basically you want to break down the problem. So for this one, let's say, what we'll do is we will first, let's just write a row number. So the row number, row number for this is 1, 2, 3, 4, right? So now what will I do is let's say I count the number of stars. So the stars I have to print here is 1. The stars I have to print in this row is 2. Stars I have to print in this row is 3, and then in this row 4, and then in this row 5. And then what I'll do is I'll try to come up with a relationship between the row and star. So in this case, I can say star is equal to 1 plus row, right? This is true for all the star and row combinations. So now if I run this, I can, let's say, try to write this. For int row is 0 to 5. For int star from 0 to, so star we saw is 1 plus row. So I'll use 1 plus row here. And then inside I will print star followed by a space. And here I will print /n. What did I? Okay, this should be a comment. Okay, so if I run this, yeah, it is printing the stars as we wanted. Now let's try a different combination. So I will, let's say, want to print the inverted triangle. So my row remains, the row is 0, 1, 2, 3, 3, 4. So what is the relationship between star and row is what we should figure out. So can someone take a guess?
5 minus row.
5 minus row.
Okay, 5 minus row. So if I go ahead and change this to 5 minus row, this should work. Okay, awesome. We are able to print an inverted triangle. So now let's say I want to also shift the triangle. And actually, to simplify, let's also remove the spaces. Okay, so any idea what yeah, okay. So basically, just printing star will not be sufficient, right? So if I just print star, if I just print star, it is not putting spaces before this, since I wanted to print a triangle like this. So what I'll do is, I also need to worry about the spaces now before the star. So what I'll do is I'll also write spaces. So spaces here is 0. Spaces here is 1. Spaces here is this is a bit tedious to write. Spaces here is 2, 3 and 4, right? So we can count. So this is basically just counting. So we counted before star, we don't want any space. In this one, we want just one space. In this one, we want 2 spaces. In this one, we want 1, 2, 3 spaces. In this one, we want 1, 2, 3, 4 spaces. Right? So then can anyone tell me how spaces and rows are related?
Equal.
Okay. So spaces equals rows. So I can write another loop now on spaces. And instead of 5 minus row, I can, I can use row and put spaces and basically print spaces. So now if I run this, yeah, this is printing. This is now printing the triangle I wanted. So let's make this more interesting. So we can, let's say I want to print a full triangle. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 1, 2. Okay, so let's say I want to print a triangle like this. So the basic approach stays the same. So in this case, number of stars is 1. In this case, the number of stars is 3. In this case, the number of stars is 5. In this case, the number of stars is 1, 2, 3, 4, 5, 6, 7. And I guess this should be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So now I have 9 stars. So spaces is still the same, so nothing changes here. So anyone wants to guess how the star and those are related now?
2 times row minus 1.
2 times row minus 1. So when I put row,
Sir,
No, sir. 2 times.
sir, I have a doubt.
Yeah.
Sir, why are we always relating these things with row? We can define another variable that we can increment or decrease. according to the loop?
Yeah, so that is a good question.
I mean, in this question, we can use another variable that has value 9 initially and decrease 2 in each turn.
Okay.
So
Yeah,
it starts
that
from
is
9 minus 2 times root.
both are valid questions, valid solutions. So this is just one way to solve it, right? I'm not claiming this is the way to solve it. So what the other comment? So we will do both. So let me do this one first.
Sir,
So
this is twice of 4 minus rho plus 1.
twice of 4 minus rho plus 1. So yeah, same thing, right? Twice of same thing, right? 9 minus 2 times rho. Okay, so now if basically I change this to 9 minus 2 times rho, I should be able to see the inverted triangle. So another comment was, why do I?
Sir, please explain how spaces come in this spaces factor for that triangle.
Yeah, so here, so basically we are counting the spaces. So as we can see before this star, there is no space, right? So that's why we wrote space equals 0. Then in this case, there's only one space. So we wrote space equals 1. Then we wrote space equals 2 because there are two spaces. And so on, right? So we wrote, so basically first you can handwrite this, like how many spaces do you need? And then we try to come up with a relationship between row and spaces. So we found that actually spaces equals rows. So we can see space is always equal to rows. And then we use this information to run the loop that many times. So in this loop, we used spaces is less than row because we found out spaces equals row. For star, we found out star is equal to 9 minus 2 times row. So that's why we used, we ran this loop to 9 minus 2 times row. The other also interesting. So the other, why should I come up with this? So this is just one approach, right? I'm not claiming this is the approach, but the other approach is also interesting. We should try that. So the other approach is, why not run two loops simultaneously? Star equals 9. So star starts from 9, and every time is this comma? Star is equal to star 9. Yeah, I don't remember if this is comma. We'll see. And say this is stars. Let's see. Okay, so this also works. So you are right. So you don't necessarily need to find a relationship between star and though, but this is just a way to do it. But the other approach is basically we iterate on the row and star simultaneously. So here stars initially were 9, and every time we are reducing it by 2. So 9, 7, 5, 3, 2. So that's why we started in the loop itself. We put stars as 9, and then we put that we are reducing stars by 2. And in the printing, we print this many stars. So yeah, both of these approaches are fine, but I personally find that code more readable. But this is just a matter of taste. It's not something that you must do. So let's look at another one and then maybe we can stop. Or we can stop here. So any questions since it's time? Any questions on this? Okay, no questions. That means.
Sir.
Mm-hmm.
Sir, I think we should use that method because that is space efficient, I guess. Because in that another method we are defining another variable, so I think that's the reason.
It doesn't, yeah, like so yeah, the comment is here we are using another variable called stars, and here we are not using another variable called stars. So actually in space efficiency, you shouldn't matter about individual variables at all actually. Because if you think about it, your memory is 4 GB ish, right? Or even 1 GB, and we are talking about just 4 bytes. So,
Yeah.
so it doesn't matter. When I think space efficiency will become more interesting when we will study arrays in a couple of weeks. But currently, don't worry about space efficiency much.
So one more thing, like over here, the spaces that are there, like they are only for the first star, like before the star, the spaces matter for only the part before the stars begin, right?
Yeah, this is for only these spaces. I guess, are you asking that we didn't consider spaces after stars?
Yeah. It's not, like even though it's equidistant, but it does not matter, right? Because the stars will only be printed
Yeah.
after the position.
Yeah, exactly. So we could print it, but we won't see any difference. So if I run this, we can print the stars, but so previously we didn't have the stars here, sorry, spaces here. Now we do have spaces here, but visually you can't really tell. So that's why we didn't worry about the spaces after printing stars.
Sir, I have a doubt which is related to runtime. Like, suppose if I'm initializing two variables, one would be long int, other would be simply int. And both of the numbers I'm giving a limit which is just int. It's not crossing int's limit. So just because I'm assigning a bigger set of data for the long int, but I'm giving a smaller number, will it matter like the speed? Like will long int and int have the same time or will it have different times?
So yeah, that is a very architecture dependent question. So if you have like 32, so long int is unsigned long int is 64 bits and int is 32 bits. So it will use less space and your operations may be faster. It's a very architecture specific question. So it's hard to make a general comment, but how your computer is used.
But like in runtime, you take the time which the compiler tries to find a set of like because it's 64 bit, it will take a single set of 64 bits, right? It can't take 3 bits from here, 4 bits from there. So it needs a single line of 64 bits. So it will take more time to search a single set of such a huge chunk of data. So will that matter in the runtime?
Oh, wait. That is a very confusing statement. So the way it works is basically your CPU has something called registers, right? So when you say you have a 64-bit CPU, that means your registers, actually, let's see if I can demonstrate this. This will become a little hard, but so basically you can actually, yeah, so this is not even CPU thing. Let me think about how I can demonstrate this. Wait. it's dash s, right? No such one. I think it's okay. I'm forgetting the command, but basically you can. This is, I did this in the. I think it's dash s. It might be something else, but when you have a program, you can see the assembly output. So this is the program we were talking about last time, x divided by plus plus x. So using a compiler flag, you can build this. This is called like assembly code of the program. And these are the registers that this assembly code is generating. So basically all the operations that you do on the variables are done on what are called registers. So for 32-bit, it might use smaller registers. For 64-bit, it might use bigger registers. But yeah, like it gets pretty complicated. Like it's hard to answer. But in general, like 32-bit, if you're using lesser space, 32 bits, that means you can put more number of integers. And that means your program potentially runs faster. But otherwise, it will have to keep going back to the RAM or the cache to bring it, do some computation, then put it back into the RAM, then bring a new number, do something and put it back into the RAM. But in our examples, we are only using 2 or 3 variables, so it doesn't really matter much. Like this is only in this program, we are only using 2 integers, 2 variables, so it's only going to use 2 registers. So it doesn't really matter that much. But for bigger and bigger programs, this can get, it's hard to simply say like how things will behave.
Okay, so thank you.
Yeah. Okay, let me see if the other professors are on the call.
Sir. Hi, Abhilash. I'm here. I think Ragesh is also here. This is Adi here.
Okay.
Great.
So yeah, please go ahead.
Yeah, so Aditeshwar, do you want to start?
Yeah, great. So hi everybody. So what we wanted is it's been more than a month now, month and a half probably that we've been in the course, and it's all very different circumstances. We're not able to meet. So Ragesh and I thought that it would be great to conduct an informal feedback session. Yeah. So we basically want to just hear from you about anything you want to talk about in the course, right? So broad feedback in terms of any particular problems you're facing, could be with remote working, could be with logistics on access to computational resources, could be with the pace at which you're going in the course. So all this feedback will really help us figure out how to improve the teaching as we go forward. Because one thing we also recognize is that there's also a lot of diversity in the class. Many of you are studying programming and working with computers for the first time, but many others have had a lot of experience. So yeah, so this is just to hear from you so that we can improve the course further going forward. Yeah. So please go ahead, folks. Any questions, anything you want to talk about, just speak up, unmute yourself, and we basically want to hear from you. Yeah.
Sir?
Yeah.
Sir, will we have time complexity analysis at some point in the course? Because it's very difficult to talk about efficiency without it.
Yeah. It's coming up. In a few classes, we'll start talking about algorithmic complexity. I think the kind of efficiency we've been talking about so far is more in terms of whether you should perform operations as integers or floating point operations, or can you make your loops more efficient, right? So that's slightly different efficiency to reduce the instructions that are being executed, but we're going to talk about algorithmic efficiency also very soon.
All right, sir.